All right, g'day everyone. Welcome to the webinar. My name's Rafe. I have my own company, I guess, at the moment where I do a bit of consulting, mostly in the industrial space, around lubricants and lubricant technology. And the guys at Southern Cross Lubes wanted me to kind of give a bit of an overview today about the changing landscape in engine oils. Hopefully we can run you through really the last 10 years, but I'll extend a little bit further back about some of the changes that have made engine oils what they are today. So we'll look at regulatory frameworks, changing market conditions, different technologies, both on the lubricant side as well as on the OEM side. And that really shapes how engine oils look today. And then we'll take a bit of a look into the future about what engine oils might look like over, let's say, the next 10 to 20 years, because as we know, technology is evolving pretty quickly at the moment. And so I think there's any number of possible outcomes over the next 20 years, and it's just a really interesting space to be in. We might as well just get stuck straight into it. If you've got questions or anything, Haley, if you wouldn't mind monitoring the chat and maybe jumping in if you think there's an appropriate question, happy to be stopped. I'm obviously going to take questions after the fact as well. And I think Haley mentioned in the chat that this is also being recorded. So if for any reason, you miss something or you need to go over it, I think it'll be available later. All right. So let's get into it. All right. So what I'm going to talk about today is, first of all, the changing regulatory landscape. And this has been a bit of an interesting story, let's say, over the last 10 to 20 years. So if we look at the sort of regulatory framework across most of the world, and we put it a bit of a timeline to it, going back to sort of the early 2000s, you've got all your different organizations that are trying to make changes. So you've got, the API, for example, with the GF and the CK ratings, or CK as they are now. Then you've got the Japanese doing the work on the JSO, and then over in Europe you've got your ASEA specifications. Obviously, China has its own set of engine oil specs as well, but they kind of all map onto each other, and everyone is roughly trying to achieve the same thing. And all of these different engine oil specs actually map onto the various emissions regulations that have been put in place by various regulatory authorities around the world. And if you had to split them up, really, in the sort of 2012 and before, that's what we would call sort of the emissions age, versus what we're in now, which is talking more about fuel economy. So why is it that I kind of split those two up? So let's look at emissions control for starters, and let's look at just the diesel engine oil specs, right? So as an example, if I were to put, there was mostly a focus on NOx as well as particulate matter. So NOx is obviously the nitrogen compounds, and particulate matter is just solid particles in the exhaust. And if you go back to what the CG4 regulations look like, when we moved on to CH4, it was a reduction in NOx. CI4 was a further reduction in NOx. And then we started emphasizing the particulate matter when we went to the CI4+. And what you can see is that the allowable window of NOx and particulate matter got narrower and narrower as we went along. And if you had to put some kind of years to it, that's really an evolution that happens from the mid-1990s right through to 2010. And obviously now we have the CK4 spec. So to just put some numbers to it, you look at the reductions, and it's absolutely massive, and it's been a bit of a game changer. Now, the oil regulations, or the self-regulation really of the industry, has gone along in conjunction with developments on the OEM side as well. So how did engine manufacturers and car manufacturers also meet all these quite stringent regulations? Well, back in the 1990s, it was all about changing piston design. Then we had combustion control measures come in, things like exhaust gas recirculation, and then SCR and DPFs. That really helped us. And then on the fuel side, we also had basically a reduction in the amount of sulfur that was in the fuel, from 500 parts per million right down to 15 parts per million, which you would call that kind of ultra low sulfur diesel. Now, if you just strip away all the detail and look at the progress that we've made from the CG to the CJ4 spec, you can see that the window of allowable NOx and particulate matter has shrunk vastly, to the point where when they came to do the CK4 regulations, they realized that most of the low-hanging fruit has already been taken up to try to reduce NOx and particulate matter from CJ to CK4 wasn't really going to help any. And so what's the only other real emission that you can start to control is carbon dioxide emissions, right? Now, carbon dioxide emissions, trying to let's say, fix those at the tailpipe is a very difficult proposition. So the reality of CO2 emission controls is that you have to move into fuel efficiency, which is just where you burn less fuel and therefore less carbon dioxide comes out the tailpipe. And if you kind of map miles per gallon or effectively fuel efficiency against years for all types of vehicles, you see a very similar trend line. And it has to do a lot with market forces as well as government forces. So, if you stretch back into the 1970s, for those of us who were around at the time, that's not myself, but some people on the call may have been around in the 1970s and have been aware of the oil shocks of that time. So when there was a period of really high oil prices, that drove the OEMs to gain much more fuel efficiency because it was in their interest, and it was in the interest of the consumer. After that, in that sort of period of the 1980s right through the early 2000s, we had relatively stable oil prices, right? We didn't have those massive oil shocks brought about by, turmoil in the Middle East, as well as the cartel behavior of OPEC, all that kind of stuff. So with stable oil prices, there was less incentive to improve mileage on vehicles. And so what we saw was that there was a relative stagnation. And from a regulatory framework standpoint, that's when you saw the emphasis on NOx and particulate matter emissions. If everyone can remember back to 2010, the oil price hit about, I think it was $140 a barrel, which is really, really expensive. And that, along with a lot of these, let's say, sustainability criteria that are being brought around, a lot more emphasis on things like climate change and government intervention, has seen requirements on OEMs become a lot more stringent, particularly in Europe. And that's where we've gone back to that fuel efficiency age, where now the OEMs are trying to eke out many more miles per gallon, or as much as they can. All right, so that's one story. Then we've also got the idea of changing market conditions, right? So, one thing that you'll notice on the chart that I put up with the emissions control is the reduction in sulfur that happened with the actual diesel. That actually happened in the lubricant space as well. So there are two triggers for that. One is that we just want to reduce the amount of sulfur, because sulfur compounds in the tailpipe can produce things like acid rain, right? If we have too much sulfur in the atmosphere, it's generally bad for the environment. The other thing that sulfur and phosphorus, which is sort of the cousin to sulfur, do is that they poison the catalysts in our exhaust systems. And so there was a move on the part of the base oil providers to move to lower sulfur compounds. Now, for anyone who's not familiar, base oils are grouped into what we call the 5 API groups. So group 1, 2, and 3 are what we would call mineral oils, right? And the distinguishing factor between those is more or less the sulfur content. So you can see over here that the sulfur content of a group 1 is much higher than that of a group 2 and a group 3. Now, 3, 4, and 5 are what is known as synthetics, and I'll get into a little bit how group 3 came to be known as or regarded as a synthetic oil. But what that really drove was a move away from group 1 oils, which were in many ways the standard in a lot of diesel engine oils, as well as passenger vehicle motor oils. And that drove us into what you would commonly call higher quality base stocks, which is group 2, group 3, and group 4. Right? So market forces helped drive engine oils away from group 1s into what we would call higher quality. I use it in air quotes because group 1s are very good in very specific applications, but in vehicles where you want a high viscosity index, so that means that the viscosity changes very little with temperature, you want a group 2 through 4. All right. Alongside that, we also have a paradigm of changing legal definitions. And in order to kind of tell this story, which is really the story of how minerals became synthetics and how marketing departments all over the world kind of screwed up the nomenclature, I've got to take you back actually sort of to the 1990s. And in the 1990s, things were much simpler. In the lubricant space and in the oil markets, a mineral was very obviously a group 1, a group 2, or a group 3 oil. And if you had something that was synthetic, right, then that very clearly referred to a PAO, which is a polyalpha olefin, a PAG, which is a polyalkylene glycol, an ester, or an alkylated naphthalene. Some genius in the marketing department at Castrol, though, decided that they wanted to market a new product, which was called Castrol Syntec, and they wanted to do it in a very specific way. And so Castrol actually ran TV ads at the time, and this was in the sort of mid to late 1990s, arguing that Castrol had what they called a unique molecular bonding. This was the actual sort of words that were used in the TV ad. And the other thing, which was pretty bold, was that they claimed that the product had superior protection to all other motor oils. Right now, this in particular kind of got up the goat of Mobil, who at the time were far and away the biggest proponents of what we would call like the traditional synthetics. So I think that the technical term for it was that they were very grumpy cat. They sort of had argued on the basis that the Castrol product had actually moved from being a full PAO to being a group 3. And so they contended, well, actually, you're not offering a better product to the consumer. The formulation is actually worse than it was before. And it's very difficult to make the claim that it's superior to everything else. So if you're not familiar, in the marketing world, when it comes to especially the big players like your Castrols, Mobils, and Shells of the world, when they make marketing claims, those have to be backed up by actual data. So if you were to say that a product offers superior protection to all other motor oils, then that would imply that you have actual real-world test data to back up that claim. And so ultimately what happened here is that they ended up going to court. The court decision is actually a really interesting one. If you're ever interested, I can send you some materials on it. But Castrol's basic argument was that when we talk about the word synthetic, they wanted to change the norms of the industry. And they said a synthetic shouldn't be how we think of it. A synthetic is effectively anything, it doesn't matter what it started as. If we are able to chemically transform it into something that is unrecognizable from the initial product, we should be able to call that synthetic. So I guess if I were to take the side of Castrol, the argument that you would make is in something like an engineered timber, right, that you use to construct a house. That has been so fundamentally changed from, its raw product, which is a tree, right? So by chopping it up into small particulates and including resins and all that kind of stuff, we have so fundamentally changed it that a tree and an engineered timber are completely unrecognizable from each other, and therefore engineered timber would be a quote-unquote synthetic product. So that was the argument that Castrol was making. On their side, they happened to have some pretty good witnesses who'd actually won the Nobel Prize in chemistry not all that long ago. And so that was a reasonably convincing argument. On Mobil's side, they said, hold up, the industry norm and what has always been understood is that synthetics are formulated from very small molecules. We subject them to a chemical reaction. These are not derived from crude oil that comes out of the ground. So as an example, with a polyalpha olefin, you start off with ethylene gas, right? So it's a very pure feedstock, if you like. And by reacting those molecules together, you can build a much larger molecule, which gets you to a PAO. And as expert witnesses, they were able to bring the EPA of the United States, so that's the Environmental Protection Agency. Funnily enough, Exxon was on their side, so you've got to remember this was pre-merger, so Exxon and Mobil were two entirely separate companies. And they also brought evidence from Castrol's own website at the time. Now, early 1990s, so the websites weren't all that great. But you can imagine that Castrol's own website was effectively saying that the synthetic definition agrees with Mobil. In the end, what happened was that I guess it was a jury ruled in favor of Castrol. And just like, Jesus turned water into box wine, they basically took that Castrol Syntec product and they gave it the blessing, and they said that's now considered a synthetic. And ever since then, Group 3s or Group 3 pluses which do start their life as a crude oil, they have legally around the world been called synthetics. I think the exception is maybe in Germany, where I think they're still hanging on to the PAO and Group 5 definition. Unfortunately, what does that mean for you guys? In the marketplace, it's made it very confusing. So you'll see terms like semi-synthetic, synthetic technology, even synthetic fortified. What do all these really mean? Often what that means is that there might be, a tiny little splash of PAO or Group 3 plus, splashed in with what is effectively a Group 2 base oil. But it's created a lot of confusion as to what is a synthetic. And, as an example, I looked at the Pennzoil website for a customer a couple of weeks ago, and every single product in their lineup is labeled as some kind of synthetic, regardless of what is actually in the bottle. Now, what's interesting about that is that, before I said market forces have driven us away from Group 1s down into the Group 2 through Group 4s. Well, now there is no incentive really to put a Group 4 PAO in the bottle anymore of an engine oil, because someone who is producing a cheaper Group 3 can market it in the same way. And so that's really driven the market away from Group 4s. And so now the vast majority of engine oils that are in the market now are a combination of Group 2 and Group 3. All right, let's talk about the next factor, which is really helping to drive changes in engine oils, and that's changing base oil technologies. So you might think that base oil technology is kind of fixed, right? We've had minerals and we have PAO synthetics. It's been like that pretty much since the 1970s, right? And there really hasn't been all that much evolution. But in fact, there's been quite a lot of moves in the base oil space, and the big player that I'll talk about here is in the engine oil market has been the rise of what we call gas to liquid technologies. So now, obviously, new technologies in the refining space are expensive. They take a lot of money. You've got to build a lot of infrastructure. So any changes do happen quite slowly. But the gas to liquids process is really predicated on the idea that you can take small molecules and turn them into larger ones. So if that sounds familiar, that's exactly how I describe the process of making a full synthetic Group 4 PAO, right? You take ethylene gas, you react them together, and you get a very pure, high VI product in a PAO. So with GTL technology, they've taken that fundamental idea and said, well, natural gas is predominantly methane. Let's use a very similar process to get ourselves to a product that looks a lot like a Group 4. So the actual chemical process that's used is called Fischer-Tropsch. You don't really need to know how it works, but just to give you the quick rundown, you take methane, water, and oxygen, you react them together, you get carbon monoxide and hydrogen. Once that moves on, you can effectively turn these into long chain waxes. And using these waxes, you can either then just sell that wax, or you can put those paraffin molecules through what's called an isomerization process, and you can get yourself either naphtha, diesel, or lubricant. Now, the biggest proponent of this is Shell. They have a huge facility in Qatar, which is I think it's called the Pearl GTL plant, and they make vast quantities of it, and they're the biggest player in the market. Now, Shell Base Oils actually sells this product into other companies in the same way that ExxonMobil Chemicals sells their PAO technology on the open market to everyone. Shell Base Oils also sells the GTL product to everyone. And so that's really changed the shape of what this chart looks like, because now you can insert another line, which is Group 3 plus, and it has it's not quite as good, but it has let's say comparable properties to a polyalpha olefin, but at a lower price point. Now, I might just jump in here just very briefly, because you're probably asking the question, well, if this is such a good technology, why isn't everyone leveraging GTL technology? And this goes, again, to tell a bit of a story, this goes back to the way that oil companies operate. You've got to remember that it's a huge investment in making a facility like this. And in fact, ExxonMobil was the original pioneer of the GTL technology, and they ended up licensing. I believe they ended up licensing and ultimately selling it to Shell. Now, the reason for that, you might think, if Shell has been so successful in promoting these on the open market, why is it that other companies haven't jumped in? So Shell have been it's been very profitable business for Shell, and actually, in many ways, the demand is oversubscribed. They actually can't produce enough GTL to keep up. So you might think, well, that's a really good thing for Shell. At the same time, times like what we're living through now is when they kick themselves that they have this GTL technology. Because let's say, for example, what's going on in Europe at the moment with extremely high gas prices. Most oil companies would much prefer to take the natural gas that they derive out of the ground, send it over to Europe, and sell it at a huge premium. That's what they really want to do. But because Shell has this refinery where they've committed to putting a huge amount of gas through the facility and turning it into GTL liquids, they kind of are constrained in doing that. And they can't raise the price because they're competing in a completely different market, which is they're effectively competing against polyalpha olefins. The other restriction on GTLs as well is that at the moment they can't really make really high viscosity grades. So if you're looking for a thicker, let's say a gear oil, for example, that'll tend to be a PAO rather than a GTL product. Okay, I think that sort of more or less covers it. Let's go back to the presentation. So the other thing that has really changed the market over the last 10 years is changing engine technologies. And you can sort of see this in the way that a lot of the new specs are built. So as an example, with the recent GF6 updates, GF6 was split into GF6A and GF6B. And one of the things that probably marks them out as being different is the viscosity grades, right? So GF6B has gone down to a 0W16, which, extremely thin. And effectively, the differences there is that GF6A is backward compatible because all of those viscosity grades already existed, and GF6B is a completely new thing, and therefore it's not backwards compatible. But between these two specs, right, combined, they make the API SP service category, right? Now, why is this new service category required? Like, what are some of the changes in engine technology which sort of precipitates new oil technologies? Well, it all comes down to this mantra of fuel efficiency. And the way that the OEMs have gone about it is to introduce a number of changes to our cars. So one thing that you'll probably have noticed is that engines are getting much smaller. So before, where a 1 to 2 liter engine would have been laughed at, these days that's reasonably common, right? One of the other things that is much more common in the modern era is turbochargers, right? You see small turbos on virtually all cars. Direct injection, stop-start at the lights. I know that's an annoyance for almost everyone, but that has become a very common technology that you really didn't see pre-2010. Hybrids, right? That's another way of getting fuel efficiency, and of course changes in the formulation. But anytime that we make these changes, there are unintended consequences. And probably the biggest unintended consequence of all of the recent changes has been LSPI. Now, I'm probably preaching to the converted here. You probably know this phenomenon much better than I do. But just to cover it, LSPI is, of course, low speed pre-ignition. And where it's a little bit different, right? I'm going to show the sort of the standard combustion cycle here, right? You expect what we would call a waveform, which looks pretty regular. And ignition happens, like the spark ignition that happens in most cars, happens a little bit after, top dead center. Now, with low speed pre-ignition, what effectively happens is that we have an ignition event that occurs before top dead center that causes a wavefront which is going in opposition to the motion of the cylinder, and that causes all kinds of vibrations, and ultimately that kind of vibration is really bad for the engine. Now, the OEMs have been working really hard at trying to pin down the exact causes of LSPI. The reality is it's still a bit of an unsolved murder, if you like, but they have been able to narrow it down to a few common causes. One of the factors is that we're running and the reason it's called low speed pre-ignition is because we're running at it tends to occur at lower speeds and higher loads. It's much more common in turbocharged direct injection engines. So again, that points to a lot of the new technologies that we've brought about to enhance fuel efficiency. But on the lubricant side, one thing that was maybe not well understood until quite recently is the fact that detergent chemistry plays a part. Now, you might be saying, what exactly are detergents and what they do? So funnily enough, the detergent in your engine oil operates much the same as does the detergents that you use at home, right? So this picture always kind of amuses people. This is not a grade 10 physical education class. But what it is basically a molecule that is trying to attach itself to polar compounds. So let's go back and review a little bit. When I use a soap in a sink, what I'm trying to do is remove grease that's on, let's say, on my plate when I'm doing the washing up. So most of the bulk liquid is water, and I want a molecule that is soluble in water but will attach itself to grease and then help the grease be washed away. Now, detergents in oils are exactly the same, but they work in reverse. So rather than everything being water, everything is oil, and they're trying to attach themselves to molecules that look like water, right? So polar compounds, and that's how detergents work. Now, detergents are, I've got the sort of the little tail. That's generally a long chain of oil, and the head, which is charged, is generally a metal, right? So there are calcium based detergents, there are magnesium based detergents, sodium based detergents, and things like that. What we found was that calcium detergents, which were far and away the most common in the industry, were actually causing LSPI. So that's driving us towards removing the calcium in a lot of formulations, and that will change how engine oils look. Now, when you look at the evolution of, let's say, the S category, from, let's say, the 1990s right up until now, we had SH, right? SJ, SL, SM, SN, SN+, which was a bit of a stopgap because SP was taking so long. And then finally, we've gotten ourselves to the SP, which is the GF6 category. Now, with SH, there was an additional one test over the previous. Then we had one test for SJ, 4 for SL, 1 for SM, 1 for SN, an additional 1 for SN+. The SP classification has required an extra 7 tests to pass. And this is all because of LSPI. So if we look at the actual tests, and the evolution from GF5, so we had the SN category. There were a certain number of tests that your oil needed to pass. SP was taking forever. So we put in an interim measure with SN+, which had one additional test to confirm that your lubricant was not a contributing factor to LSPI. And then with SP, we introduced a whole raft of different changes. And they're all driven by very specific things that we're trying to accomplish. So we're trying to get better fuel economy. So remember I said we are in the fuel efficiency age, right? Everything about engines and lubricants is about trying to improve fuel economy. We also want LSPI protection because that was an unintended consequence of a lot of the changes the OEM has made. We want chain protection, improved cleanliness, and better high temperature viscosity control. So some of the engines are running at higher temperatures now. That oxidizes the oil faster and could potentially cause more deposits in the system. So that's why we want to improve the cleanliness of the formulations. So what does that mean going forward? So for better fuel economy, ultimately it's going to lead to lower viscosities. I remember the first time that I heard that there was a 0W20 in production. That seemed completely insane to me. Now we have a 0W16. So lower viscosities, so if you have a less viscous fluid, the engine has to do less work to move that fluid. And because we lose less energy, that results in better fuel economy. For LSPI protection, what you're going to see in terms of changes in the formulation, so if you did an oil analysis test, you'll see less calcium and much more magnesium. For chain protection, you're going to see more ashless anti-wear. So that's part of a move to reduce the amount of ZDDP. So whenever you hear the term like high zinc, what that's referring to is a molecule called ZDDP, which stands for zinc dialkyl dithiaphosphate, the most common anti-wear additive in the industry today. The problem with ZDDP is that ZDDP contains both sulfur and phosphorus, and both sulfur and phosphorus poison catalysts. So there has been a move over time to reduce the amount of zinc, right? But unfortunately, if you reduce the amount of zinc, you have to protect things like your cams in some other way, and so you have to include, more exotic anti-wear additives. On the improved cleanliness side, there's a move to better solvency and improved detergents. So detergents help clean up the system, but you also want better solvency. So the ability to, carry deposits in solution. And so that's driving us, you'll see a lot more things like esters in a lot of the new formulations. It also encourages more dispersants at higher weights, which is a pretty similar additive to detergents. Finally, for better high temperature viscosity control, we really need to move towards higher quality base stocks. So group 2 base oils are becoming even less common than they were before. And really, the engine oil market is dominated by group 3 and group 3 plus at the moment. You'll also see more synthetics. So that's the sort of group 3 and group 3 plus. And I personally think that there's actually going to be a bit of a move back towards PAO again. Especially because the market for group 1 is starting to die off, and it's, in the industry is being replaced in the supply chain by a lot more PAO. All right. So hopefully that's given you a bit of a primer for all the changes that have happened. I know it was a lot, and I'm speaking, quite quickly, but there are a huge number of changes that make the oil that you have in your car today look the way it looks, right? So it's external forces as well as innovations within the industry. Now that really kind of begs the question of what does the future look like? And I think this is a really fun question to ponder, because ultimately it could go any number of different ways. One of the options that no one really talks about is that things just kind of continue as they are, right? That is entirely a possibility, although the rate of technological change makes that, I would say, a very low likelihood outcome. Where I see there being, huge potential changes is a move towards bio-based and biodegradable lubricants, right? So we saw this a little bit in the fuel industry where everyone tried to move to bioethanol, but I can see it happening in lubricants. Now, there's a couple of downsides to that happening. Basically, all plant-derived lubricants are esters, right? So a lot of synthetic esters, for example, you should have probably heard the term before, like the idea of a synthetic ester. They are usually plant-derived, right? So all of the oils that lubricate jet turbines, for example, I think originate as palm oil for the most part. Now, there are two big downsides of esters. One of them is that they're known to swell seals. And the other one is that they're very unstable in the presence of water. But new technologies have kind of found their way around this. So with seals, right, seals are actually, their chemistry is almost as complex, if not more complex than lubricants. So they're a mixture of also a base material as well as a whole raft of different additives. And you can think of them as being a little bit like a matrix. And so in order to swell a seal, the molecule of liquid lubricant has to be able to pass through that matrix and then enlarge it. Now, there are a couple of ways that we can tweak the molecule to prevent that from happening. And one is just to change the shape. So double bonds tend to bend the molecule, and this means that if it tries to get through the matrix, it's just going to butt up against it. And the other way that we can do it is just to increase the size of the molecule. And so there are some really interesting and innovative companies. I talked to one in the US called Biosynthetic Technologies, where they are taking esters and they are making them so large that they actually can't fit through the seal matrix, and therefore they don't swell seals. If anything, they actually shrink them a little bit. So that is a sort of an interesting development which makes bio-based lubricants a little bit more feasible. The other thing that they've been doing is to fix the water stability. So this is called hydrolytic stability, where basically if water gets in with an ester, it causes it to break apart and it forms an acid. And obviously acids are not a desirable thing to have in your engine. So where water attacks is it tends to attack these various oxygen groups. So what I'm showing here is a polyol ester, but you don't really need to know that. So it tries to attack the oxygens. So where a lot of the innovations have been is how do I change all of the sort of the hydrocarbon chains around those oxygens to kind of, in American football terms, it would be like having blockers, right? To try and prevent the water from accessing the oxygen purely because of the geometry of the molecule. And so by doing that, they've made them actually very stable in the presence of water, which is something that's really exciting. One change that I think we're going to continue to see, in some ways, unfortunately, right? One thing I think we're going to see in lubricants is lower and lower viscosities. And what's coming is 0W8. I couldn't believe this when I first read about it 2 years ago, but it looks like, especially the Japanese manufacturers are looking at introducing a 0W8 spec. I think it has been formalized, and there are a handful of companies that are selling 0W8, but that's a very low viscosity. And I've got questions about how things like the cams are going to hold up. So what that ultimately means is that because the lubricants are getting thinner and thinner, it means that the additive package is going to have to do a lot more work than it used to, right? And so this is really driving huge changes in additive chemistry, which I think is a really interesting area of research and development that's going on at the moment. What's generally happening in a lot of the engine oils is that the actual base oil, which we used to rely on to lubricate all our components, that's starting to take a back seat. And we're having all these much more exotic chemistries being developed by the additive companies to try and protect a lot of the engine components. So we're seeing a lot more, molybdenum being used, some barium salts, a lot more boron, and a lot of that is to fix these changes. It's also being designed because as we reduce the amount of ZDDP, zinc is this fantastic molecule because aside from poisoning catalysts, it acts as an anti-wear additive, so it can help protect, your cams and your chain and your gears and your oil pump. But it also acts as an antioxidant, so it has this dual purpose, and that's why it's been far and away the most popular additive. Replacing that is quite a challenge because there aren't that many molecules that can perform those dual functions, and certainly not at the kind of cost point that ZDDPs have always been able to meet. All right, and then kind of the other one that we need to really talk about, and this is sort of the elephant in the room, is the EV market, right? And of course, if you've been following the news, the Tesla share price has been going absolutely ballistic over the last couple of days. You probably would have seen, I think it was yesterday, that Hertz, the car rental company, placed an order for 100,000 of them. So it feels like the EV wave is finally coming. The good news is that a lot of the legacy automakers are also kind of jumping on board as well and coming up with some really interesting and new technologies. So the Porsche Taycan, for example, I think is a really good example of this, where they've done their best, from what I've read. Just let it be known that I've never driven one and I will never own one because, cost. But it seems like they've done everything that they can to sort of retain that Porsche feeling and that brand awareness, but bringing it to an EV platform. So I think there's potentially some exciting stuff to happen in this space. But what is interesting about the EV platform is that they're more or less the same under the hood, right? You kind of have a skateboard platform. You've got the motor. Sometimes there's only one motor and it's rear wheel drive. Sometimes there's two. Sometimes there's four. But they all look, roughly the same under the hood. And obviously, the Volkswagen Group has taken advantage of this. And I think, the new Audi e-tron is effectively the Porsche Taycan underneath, just with a different badge and a different chassis on it. So now the question is, what role do lubricants have in an EV world? And surprisingly, there's actually quite a lot. So some of the things are going to be retained from the previous age of vehicles. So, fluids for your steering rack and your greases for your wheel bearings and all that kind of stuff, that all stays exactly the same. There's really not that many changes. The only thing that I would say is that there is much more emphasis now on efficiency, because EVs these days are sold on range, right? So if you can lower the viscosity of the wheel bearing grease to help it go an extra couple of kilometers, then the EV companies will do that. The other really interesting developments have been around the battery cooling technologies. So there is a bit of an ongoing debate at the moment about what kind of fluids do we use for battery cooling. So you can really take a couple of different approaches to that. So the original Nissan Leaf, for example, no cooling technologies, completely passively cooled. They just ran air over the system. That's probably not optimal. Then you've got a whole bunch of companies that are cooling the battery with standard water-based, water glycol lubricants. And then you have companies like Porsche, which are trying to integrate the battery cooling in with the electric motors and using one fluid that is an oil-based system. And the advantage of an oil-based system is that lubricants are what we call dielectrics, so they don't conduct electricity, which means that you can have them in and around battery components without the battery shorting out. So again, that's a bit of an open question as to which technology wins. And then finally, you've got the transmission and the motor, and the requirements for these are quite different too, because some of the time they integrate the transmission and the motor, so you've got to protect both the motor and the gearbox. And as far as formulations and things like that go, you often have competing interests. So as an example, if you compare the requirements of, let's say, the motor to the battery, what you really want for the motor and the battery is a very, very thin fluid. Because if I want to carry as much heat around the system as I can, I want something that's very thin and flows very readily, right? That helps carry heat away. But if I'm also lubricating the transmission requires a gear oil that is at a much higher viscosity at high temperatures. So how do I balance the two of those requirements out? Again, that's a little bit of an open question. And the other thing that's kind of in conflict is that for the transmission, you want, an anti-wear additive like a zinc, but that's incompatible with the copper that's in the motor windings. So again, formulators are trying to have to come up with creative ways to come around that. The final bit of new technology, which is again a bit of an open question as to how this technology looks, is of course hydrogen. So at the moment, I think a lot of the press and the excitement has been around the idea of hydrogen fuel cells, right? So you take hydrogen probably in liquid form, it gets stored in a canister, and that helps charge a fuel cell, right? And then from then onwards, it effectively works like an EV. But there are also changes afoot because some of the the industrial gas engines, like the likes of your Jenbachers and your Waukeshas and things like that, they are actually moving towards hydrogen ignition engines. So exact same engine, but instead of putting natural gas through it, you put hydrogen. And again, a lot of formulation changes required for that, and changes in engine technology, because the flame temperature and the flame speed of hydrogen are very different to methane and crude oil derived products. So that's one big change. But also when you combust hydrogen, you get water. So we're going to have a lot more water in our engines, and how do you deal with that water and how do you filter it out? That could potentially become a problem with hydrogen ignition engines. Anyway, so that kind of wraps up everything that I had prepared to talk today. Hopefully that's given you two separate pictures, right? A bit of a story of how engine oils evolved, let's say over the last 10 to 20 years, and how that got us to where we are today in an age where synthetics are quite important, but their definition is a bit up in the air. We also have a lot of changing chemistries which are involved, and a lot of that is driven by the fact that all the OEMs are after fuel efficiency, right? Fuel efficiency has become the king, and that's a bit of a mantra going forwards. And then how do engine oils look in the future? There's obviously still going to be a lot of demand for it because there's a huge heritage fleet, and people are continuing to buy petrol vehicles. It's not like EVs have taken over yet. So there's a lot of work to be done on the petrol and diesel side. But as we start to get into new technologies, there is still a place for lubricants and lubricating oils. It's just that the volumes are going to change a little bit, and it will probably be into sort of more niche, kind of higher margin products. So anyway, I hope that's been helpful for you, and obviously I'm happy to take as many questions as we have.